Welcome back to the Deep Dive.
Good to be here.
It is Thursday, February 19th, 2026. And I have to say, looking at the tech landscape this morning, I am getting just a massive case of whiplash.
It is a confusing morning, isn't it? I mean, depending on which newsletter you open first today, the world is either ending or just beginning.
Confusing is an understatement. Like, if you read one set of headlines, we've finally arrived, the future is here, quantum computers are shipping, they're solving real problems, the hardware is physically in the room, it's all champagne and ribbon cuttings.
Right.
But then you flip the page to the other golden child of the 2020s, artificial intelligence, specifically in the high-stakes world of medicine, and it looks like it's waking up with a massive pounding hangover.
That is the perfect way to frame it, a hangover. We are seeing two massive technological waves crashing in completely opposite directions right now. You have quantum claiming to crest, hitting that elusive advantage stage we've been promised for a decade, and you have AI drug discovery crashing hard into the rocks of economic and, well, biological reality.
So our mission today for you listening is to cut through the noise. We aren't just reading the press releases, because let's be honest, the press releases are mostly fiction at this point.
Yeah, they really are.
We're going to look at the actual state of the union for AI and quantum as of right now, February 2026. We've got a huge stack of sources here. We're talking industry reviews of pharma from 2025 that are brutally honest.
Very brutal.
Technical papers on quantum simulation that challenge the very need for quantum hardware. And some heavy math on how encryption breaking actually works.
Yeah, we're going to move past the breakthrough buzzwords. I want to look at the actual mechanics. Why are AI drugs failing in the clinic? What is the actual mathematical probability of a quantum computer cracking a code? Because the reality is so much messier than the marketing.
But arguably more interesting.
Always more interesting. The truth usually is.
So let's start with the hangover. We have this comprehensive review from Drug Target Review. It's titled AI in Drug Discovery, 2025 in Review. Now, if you rewind to, say, 2023 or 2024, the pitch was that AI was going to cure all diseases, slash costs, and basically make the traditional pharmaceutical timeline obsolete.
That was the venture capital pitch, right? Give us $1 billion, we will simulate the biology, and out pops a cure. It was the absolute peak of the Silicon Valley can-fix biology era.
Right.
And to be fair, the technology has advanced, the algorithms are definitely better. But 2025 was the year the industry moved from promise to proof, and the proof was, well, let's call it complicated.
The report calls it a sobering reality check. But before we get into the gloom, let's talk about the one big win. Because there was one. The first fully AI-designed drug completed phase IA trials for idiopathic pulmonary fibrosis. And when we say fully, we mean the target and the molecule were designed by AI.
Right. This is a significant milestone, technically. We really shouldn't gloss over it. Idiopathic pulmonary fibrosis, IPF, it's a nasty disease. It's essentially scarring of the lungs that progressively suffocates you. The tissue thickens, it becomes stiff. There is no cure, and the current treatments just sort of slow it down a little.
And this drug, which was designed entirely by AI algorithms, showed, quoting here, a dose-dependent improvement in forced vital capacity.
Yeah. So in plain English, the patients who took the higher dose could breathe deeper and move more air than those on the placebo. That is a genuine efficacy signal. It suggests the molecule is actually doing what the AI predicted it would do, binding to the target and stopping the fibrosis.
And the speed was the major selling point here. They reached the preclinical candidate nomination in just 18 months. The source points out that traditional methods usually take 3 to 4 years. So AI cut the early discovery time completely in half. That sounds like a massive victory. So why isn't the industry popping champagne?
Because of the N number, the trial only had 71 patients.
71. That seems, dangerously low for a victory lap.
In the world of clinical statistics, 71 is a whisper, not a shout. It's enough to say, hey, something might be happening here, but it is nowhere near enough to prove safety and efficacy to a regulator for a global rollout. It needs validation in much larger cohorts. Phase 3, that takes years.
And that brings us to the actual bottleneck that AI hasn't solved. You can speed up the finding the molecule part by 30 or 40%. But you cannot speed up the biology.
Exactly. You cannot write an algorithm that makes a human body metabolize a drug faster.
Right.
You cannot compress the 6 months you need to wait to see if a side effect develops in a patient. You cannot optimize patient recruitment in rural areas with a GPU. And the broader data from 2025 really bears this out. The report highlights a brutal statistic. AI has not improved the industry's clinical failure rate yet. It's still hovering around 90%.
That is the number that jumped out at me from the source. A 90% failure rate. So you can invent the drug twice as fast, but if it still fails 9 out of 10 times in phase 2 or phase 3, you haven't actually fixed the business model. You just failed faster.
Yeah, and fail fast is a Silicon Valley motto, not a pharmaceutical one. In tech, failing fast costs you some server time and maybe some pizza. In pharma, failing fast in phase 2 still costs you $40 to $100 million. And this failure rate is why the financials are looking so skewed right now. We need to talk about biobucks.
Ah, yes, the economics of hope. This is my favorite part of the report because it exposes the financial engineering behind the scenes. The report says that in 2025, the total deal value for AI drug discovery partnerships exceeded $15 billion. That sounds massive.
It's a vanity metric. It's totally a headline number designed to pump stock prices.
Because when you look closer, the upfront payments, like the actual cash changing hands today, were only about 2% of that $15 billion.
That is a 50-to-1 ratio. It is a glaring signal of skepticism from the industry. Think about it. Big Pharma is effectively saying to these AI startups, we will put out a press release saying we might pay you $1 billion eventually, but today, here's $20 million. Keep the lights on. You get the rest if and when the drug actually works in a human.
It's essentially a lottery ticket.
It is performance-based pay on a massive existential scale. And because of that disparity, because the cash wasn't actually flowing, we saw a lot of corporate fallout in 2025. Companies shutting down, delisting from the stock exchange, cutting workforces by 20 to 30%. The market realized that technological sophistication, having the coolest neural network or the biggest transformer model, it just doesn't automatically equal clinical validation.
It turns out you can't cure cancer with a press release.
Shocking, I know.
And on top of the money drying up, you have the regulators stepping in. In January of this year, January 6, 2026, the FDA issued new guidance. I found this fascinating. They specifically focused on AI for regulatory decision-making, but they explicitly excluded early discovery.
That distinction is so crucial. It tells you exactly how the FDA views risk. The FDA is saying, we don't care if you used AI, a Ouija board, or an abacus to find the molecule in your lab. That's your business. But if you are using AI to decide if a patient is getting better, or to analyze safety data, or to determine who gets into the trial, that is our business.
They established a 7-step credibility assessment. Basically, you have to prove your AI isn't hallucinating. But there was a bit of irony in the report regarding that. It mentioned that the FDA's own internal generative AI tools had issues with hallucinations.
Which is a perfect microcosm of the problem. If the regulators' own tools are making things up, imagining side effects that aren't there or missing ones that are, you can absolutely understand why they are being hyper-cautious about approving AI-driven medical decisions.
It's like a driving instructor failing you because they crashed their own car on the way to the test.
Precisely. However, they did qualify a cloud-based tool for scoring liver biopsies in NASH trials. So there is progress. It's just not the AI cures everything overnight narrative we were sold.
So AI is in the trough of disillusionment, to use the Gartner hype cycle term. It's doing the hard work, hitting walls, and finding out biology is messy. But let's pivot. Because while AI is licking its wounds, quantum computing is strutting into the room wearing a tuxedo. According to our next source, 2026 is the year quantum finally beats classical.
This comes from a report on IBM's roadmap and the broader industry landscape. And the tone here is very different. It is aggressive. It's very confident.
The headline is, IBM says 2026 is the year quantum computing finally beats classical. And they aren't talking about a lab experiment. They are using the term quantum advantage. We used to hear quantum supremacy. Is there a difference, or is this just branding?
There is a subtle but really important difference. Supremacy was the academic term. It meant doing something a classical computer couldn't do, even if that something was totally useless, like generating random numbers or sampling a weird distribution. Advantage is the business term. It means solving a specific practical problem better, faster, cheaper than a classical supercomputer.
And IBM is claiming their Heron R2 processor is the hardware that crosses that line.
Right. They hit 156 qubits with the Heron R2. But looking at the specs, the impressive number isn't the qubits, it's the runtime efficiency. The report says workloads that used to take 122 hours are now running in 2.4 hours.
That is a massive jump. That's the difference between waiting a week for an answer and getting it over a long lunch.
Exactly. And that speed is what businesses care about. If I can optimize a portfolio or a global supply chain in 2 hours instead of 5 days, that fundamentally changes my operational tempo.
And they have a roadmap that goes even further. They are talking about the Kookaburra processor in 2027 with over 1,000 qubits and Starling in 2029 with 200 logical qubits.
Hold on, you emphasize logical. We need to distinguish that from what we have now.
Please do, because I see qubits thrown around all the time, and sometimes it's 50, sometimes it's 1,000, but apparently they aren't all equal.
Think of physical qubits, the ones we have right now, like a choir where everyone is a bit tone deaf, easily distracted, and prone to sneezing. They are noisy. If you want them to sing a clear note, you need 50 or 100 of them screaming the exact same thing so you can average out the noise and figure out what the note is actually supposed to be. That's error correction.
So a logical qubit is what, the soloist?
A logical qubit is the result of that choir working together to create one perfectly pitch-correct tone. It is a stable, error-corrected unit of information. Getting to 200 logical qubits is the holy grail. That's when you can run really long, complex algorithms without the whole calculation collapsing into static. IBM's Starling, aiming for 200 logical qubits, is a massive declaration of intent.
And it's not just IBM. The UK government is throwing serious money at this. £670 million committed over the next decade. They want 15% of the global quantum market by 2033.
It's a strategic play. They see this as infrastructure, the same way they saw fiber optics or 5G. And we are seeing the use cases solidify. Logistics, routing supply chains by analyzing all possibilities at once via superposition. Pharma, simulating molecular interactions, which circles back to our AI discussion. Finance, portfolio optimization.
There was also a note in the source about the convergence with 5G. I hadn't really thought about that connection. The idea that 5G acts as the nervous system for the quantum brain.
It makes a lot of sense if you think about where these computers actually live. A quantum computer is a massive refrigerator. A dilution refrigerator kept at near absolute zero. It's not going to be sitting on your desktop. It will be in a data center, or probably in a bunker somewhere. So if you want to use that power in real time, say, for autonomous vehicle routing or smart grid management, you need a low latency pipe to get the data to the quantum processor and back instantly. That's 5G. Without the pipe, the brain is completely isolated.
Okay, so the quantum narrative for 2026 is, we have arrived, but, and there's always a but, on this show we have another source here that throws a massive wrench into that narrative. It's a paper from Open Review titled Classical Simulation of Quantum Circuits Using Reinforcement Learning.
This is where it gets really interesting. This is the battle for supremacy. And it turns out the classical computers aren't going down without a fight.
So let's go back to 2019. Google claimed quantum supremacy with their Sycamore processor. They said it performed a calculation that would take a classical supercomputer, specifically the Summit supercomputer, which was the absolute beast of the time, 10,000 years to match.
That was the mic drop moment for the industry. 10,000 years versus 200 seconds. It felt like the end of the classical era.
But this new paper says not so fast. A team of researchers used reinforcement learning, essentially AI, to optimize the way a classical computer simulates that quantum circuit. And they got the time down from 10,000 years
To less than 4 days.
to less than 4 days.
Just let that sink in for a second. 10,000 years to 4 days. That is a reduction of orders of magnitude that you rarely ever see in science. Usually you fight tooth and nail for a 10% speed up. This is a complete demolition of the previous estimate. They reported a 5.40x speed up over state-of-the-art heuristic methods.
How on earth did they do that? Did they just get a way bigger computer?
No, they used the exact same hardware. They just got a smarter algorithm. It comes down to how you handle the math. Simulating a quantum circuit on a classical computer is basically a giant multiplication problem. You are multiplying tensors, multidimensional arrays of numbers.
Tensors. Like matrices, but with more dimensions.
Exactly. Imagine a Rubik's Cube of numbers. Now imagine you have to multiply 100 of them together. The order in which you multiply them matters immensely. If you multiply A and B first, the result might be a tiny, manageable matrix. But if you multiply B and C first, the intermediate result might be so huge it crashes your memory.
So it's a puzzle. You have to find the perfect sequence of multiplications to keep the memory usage low.
It's called the Tensor Network Contraction Ordering Problem, TNCO. Think of it like a traveling salesman problem. You have to visit all these cities, meaning you have to multiply these tensors, and you want to find the absolute shortest, most efficient route.
And the number of possible routes is astronomical.
It is a combinatorial nightmare. There are more possible paths than atoms in the universe. A human cannot figure this out. Even a standard heuristic algorithm struggles.
So enter the AI.
Exactly. What these researchers did was incredibly clever. They mapped this abstract math problem to a physics model. a K-spin Ising model.
Okay, you're getting technical. What is a K-spin Ising model?
Let's simplify it. Think of a bunch of magnets flipping up and down, trying to find a stable energy state where they are all happy. It's a model of interacting spins. They mapped the tensor multiplication problem onto this magnet model, and then they unleashed a Hamiltonian-based reinforcement learning algorithm on it. The AI learned to flip the magnets, or rather find the absolute most efficient path to multiply the tensors.
So they used AI to make the classical computers smarter, so it could simulate the quantum computer faster.
Precisely. And this leads to a fascinating dynamic. Every time quantum hardware improves and says, look, we're faster, the classical algorithm developers say, wait, we can optimize our code better using AI, and they catch up.
It's a race where the finish line keeps moving.
It raises a profound question. Is quantum supremacy a fixed point? Or will classical computers, aided by AI, constantly nip at the heels of quantum performance? If I can simulate your quantum circuit in 4 days on a classical cluster using this AI trick, do I really need to buy your multi-million-dollar quantum fridge?
That is the trillion-dollar question. If simulation gets good enough, the market for the hardware might shrink to only the most impossible problems. And speaking of impossible problems, that connects perfectly to our next section, because one of the main reasons people want quantum computers, one of the few things we know classical computers struggle with, is breaking encryption, specifically RSA encryption.
The Shor's algorithm doomsday scenario.
Right. We have a paper here from Arkivkov called Success Probability in Shor's Algorithm. And I think for a lot of people, Shor's algorithm is viewed as a magic button. You press it, and the encryption breaks.
That is the movie version. The hacker types furiously, hits enter, and a progress bar goes to 100%. The reality, as this paper details granularly, is that Shor's algorithm is probabilistic. It relies on quantum mechanics, which is inherently about probabilities. It is not a magic wand. It is a process that can fail.
So let's go under the hood for you listening at home. The paper breaks it down into 3 steps. Walk us through them, keeping it as painless as possible.
Step 1 is classical and easy. You pick a random integer, let's call it a. You just pick a number that is smaller than the number you want to factor. Step 2 is the quantum magic. You use something called quantum phase estimation to find the order of a. Let's call that r.
An order just means how many times do I multiply a by itself before I get back to 1.
In modular arithmetic, yes. Imagine a clock. If a is 5 and the clock size is 12, how many times do I multiply 5 before the hand lands back on 1? Finding that number r is incredibly hard for classical computers if the clock is huge, like 2048 bits huge. That's the secret sauce. Quantum computers can find r efficiently using superposition.
Okay, so the quantum part gives us r. Then what?
Step 3 is classical again. You use that r to do some greatest common divisor calculations and hopefully outpop the factors of your big number, breaking the code.
Hopefully being the operative word there. The paper identifies specific failure cases where this just doesn't work.
Right. The algorithm fails if the r you find is odd. It just doesn't give you the factors. It also fails if a specific mathematical condition is met. That condition is if a to the power of r over 2 is congruent to -1 modulo n.
I see some eyes glazing over. What does that mean practically?
It means that depending on the random number a you picked in step 1, you might get a dud result. The paper goes into very specific failure scenarios. For example, if the number you are trying to factor is 2, the algorithm fails at step 2.
Well, factoring 2 isn't exactly high on the NSA's priority list.
True, but it also fails at step 3 if n is a Fermat prime power. But the really interesting contribution of this paper is that they derived a closed-form formula to predict exactly how often it will succeed. For n equals 2 to the k, success depends heavily on avoiding specific trivial solutions.
So we can know the probability before we run it.
Yes. They suggest a routine to simulate Shor's success to benchmark resources. And for most numbers we care about, like the product of 2 large primes used in RSA, the success probability is quite high, usually over 50%. But it's not 100%.
So even when we have the hardware that IBM Heron or Kookaburra breaking encryption isn't click and done, you might have to run it a few times.
Exactly. You run the circuit, measure the result, check if it works. If not, run it again. This is why bounded error is such a key concept in quantum complexity. You don't need to be right every time. You just need to be right often enough that you can check the answer efficiently. If you have a 50% success rate, you only need to run it maybe 10 times to be 99.9% sure you'll get the answer. We can mathematically predict exactly how often a quantum computer will succeed before we even build one big enough to try.
This brings us to the theoretical landscape. We have a lecture source here from CMU about quantum complexity theory. And this is where the alphabet soup comes in. PNP, BQP. Help us navigate this map because I think understanding the sandbox helps us understand what these machines are actually for.
Okay, let's visualize a sandbox. The smallest circle in the middle is P polynomial time. These are problems solvable efficiently by a classical computer. Multiplication, sorting a list of names, checking if a graph is connected.
Easy stuff. Stuff my laptop does without thinking.
Then you have BPP, bounded error probabilistic polynomial time. Imagine a computer that can flip a coin. It has randomness. It can solve a few more problems than P, or at least solve them faster using statistical tricks. This is where a lot of Monte Carlo simulations live.
Okay, so computer with a coin toss.
Then you have BQP, bounded error quantum polynomial time. This is the quantum sandbox. It is the class of problems a quantum computer can solve efficiently. It includes everything in P and likely everything in BPP. But it also goes outside those circles. It includes factoring Shor's algorithm and simulating quantum systems.
So BQP is the land of things quantum computers are good at. And the hierarchy is P is a subset of BQP, which is a subset of PS space.
Yes. But here is the nuance that people miss, and it drives computer scientists crazy. BQP is not proved to be bigger than P. We believe it is. We strongly suspect quantum is strictly more powerful, but we haven't mathematically proven it.
That would be a plot twist. If it turned out quantum computers weren't actually more powerful than classical ones, we just weren't smart enough to write the classical code yet.
That is the exact argument the classical simulation paper we discussed earlier hints at. Maybe BQP is just P in a disguise we haven't cracked yet. But most experts agree BQP is larger. Now, the coin flip nuance in BQP is crucial. Algorithms must have a probability of error less than 1/4. This bounded error means you run the circuit multiple times to be sure. Now, the lecture introduces another class, PP, probabilistic polynomial. This is a weird one.
Wow.
In BQP or BPP, we demand that the computer gives us the right answer with a high probability, say less than a 1/4 error rate. That way, if we run it a few times and take the majority vote, we are almost certain to be right. In PP, you only need a probability strictly greater than 1/2. It could be 50.0000001%.
That doesn't sound very useful. If I have to run it a billion times to be sure, that's not efficient.
Exactly. PP is a strange class. But there's a weird fact about it. It is closed under complement. It contains both NP and co-NP. And the connection here is that BQP is contained within PP. It helps us map out the hierarchy theoretically.
So the map is P is inside quantum, and quantum is inside the set of all hard problems. But quantum does not solve everything. It doesn't solve NP-complete problems perfectly, right?
Correct. That is the biggest misconception. Quantum computers are not magic. Try every possibility at once, machines for NP-complete problems. They are specialized tools for specific structures, like period finding in Shor's algorithm. If a problem doesn't have that hidden structure, a quantum computer might not help much at all.
Okay, so we've covered the drugs, the hardware, the simulation wars, and the complexity theory. Let's talk about the people, because all this tech needs humans to run it.
Right.
We have a great blog post from Penny Lane, which is a quantum software library, and a Reddit thread from a software developer asking, do you think quantum computing will destroy jobs?
This is a very real anxiety. You see it in the Reddit thread. Comparing the sentiment 10 years ago versus now, the shift is clear. It went from, oh, it's experimental, don't worry, to, oh, wow, it's growing.
One of the best analogies I saw in there was the airplanes versus space travel comparison.
Yes, that's a great one. The idea is that quantum computers won't replace classical computers for everything. You don't take a spaceship to go to the grocery store. You take a car. Classical computers, the cars or airplanes, will still run your OS, your word processor, your web browser. You aren't going to check your email on a QPU. Quantum space travel opens up new territories like factoring large primes or simulating molecules, but it doesn't replace the old mode of transport.
So for the software developer listening to this who works in Java or Python and is freaking out,
Don't freak out, but do get curious. The Penny Lane blog has a great case study of a guy named Matthew Silverman going from classical to quantum as a software developer. He was a standard computer engineer working a classical software job. He had a eureka moment, realizing he didn't use math and science in his daily dev job, and he really missed it. He felt like a code monkey, just gluing APIs together.
and he made the pivot.
Yeah.
But the key takeaway was how he did it. He didn't go back and get a PhD in physics. That's a huge myth.
No. The reality is you don't need the PhD. You need linear algebra.
matrices and vectors, the stuff we talked about with the tensors.
Exactly. That's the language of quantum. If you know linear algebra, you can understand qubits and superposition. You don't necessarily need to understand the underlying superconductor physics, just the mathematical logic of the gates. It's logic, not magic.
And there are resources now. The source mentions the Mike and Ike textbook, Nielsen and Chuang, Scott Aronson's Quantum Computing since Democritus, and the Penny Lane Codebook for Interactive Learning.
Yes. And Silverman gave a great piece of practical advice. Gretzky the industry. Take many shots. Apply for jobs even if you don't feel 100% qualified. He got into the industry through a cloud role at a quantum company. That's a great backdoor. Quantum companies need websites, databases, and cloud infrastructure just like everyone else. Once you're in the building, you can learn the quantum stack.
Because we are in a new paradigm. Transitioning from binary bits as 0 and 1 to qubits and superposition. And the languages are evolving. We aren't just writing raw assembly code anymore. We have Qiskit, Q-sharp, Quipper.
It is becoming more accessible. We are transitioning from the physicist era of quantum computing to the engineer and developer era. The abstraction layers are being built. The tools are meeting the developers halfway.
So let's bring this all together. It is Feb 2026. We are in a trough of disillusionment for AI drug discovery. It's harder than we thought. The economics are tough, the clinical trials are slow, and the FDA is watching closely.
While simultaneously we are entering the slope of enlightenment for quantum. Hardware is actually shipping. IBM and massive government funding are pushing us toward advantage.
But the two fields are merging. We're using AI, specifically reinforcement learning, to simulate quantum, and using quantum to process AI workloads. It is a convergence. We used to think of them as separate lanes. Now they are merging into a hybrid compute stack.
And for the listener, the takeaway is don't buy the hype blindly, but don't ignore the progress. The fact that we can mathematically predict the success rate of Shor's algorithm, or that we have a 156-qubit processor running stable jobs, is incredible. But biology is still hard, and math is still stubborn.
Absolutely. The laws of physics and the complexity of biology are the ultimate arbiters. No amount of venture capital changes that. I want to leave you with a thought, based on that simulation paper. If a classical computer, using advanced AI, can simulate a quantum circuit in 4 days, something Google thought would take 10,000 years, at what point does this simulation become good enough that we don't actually need the quantum hardware for certain tasks?
That is the provocative thought. Are we racing towards a finish line that AI keeps moving further away? If AI makes classical computers 1,000,000 times more efficient at simulation, the quantum advantage might be a much smaller target than we thought.
A moving target indeed. Something for you to mull over or explore on your own. That's it for this deep dive into the state of AI and quantum in 2026. Thanks for listening.
Thank